Hi everybody, this is Jithin P N, Assistant Professor, Department of Mechanical Engineering, Rajagiri School of Engineering and Technology, Kochi. So this audio lecture is on the topic whirling of shaft. This topic is included in the module 6 of the course ME304 Dynamics of Machinery. This course is offered for 6th semester mechanical engineering students. So let's move to the question. Whirling is the uneven vibration in the direction transverse to the axis of rotation of the shaft. We can see here a shaft which is attached or which is mounted on onto bearings. You can see here these are the bearings. The shaft is at the middle of the shaft there is a rotor. If the centroid of the rotor or the geometric center of the rotor is not aligned with the axis of rotation of the shaft, it will create uneven vibration when the shaft starts rotating. The reason for this uneven vibration is the centrifugal force created due to the eccentricity between the centroid of the rotor and the axis of rotation of the shaft. So this speed at which this shaft is rotating, and it leads to the vibration or a violent vibration in the system in the transverse direction. Such speed is called whirling speed. Otherwise, it is called as critical speed also. So we can say this speed is the speed of the shaft at which the resonance occurs. We know that resonant condition happens when the excitation frequency is equal to the natural frequency of the system. Excitation frequency means the frequency of the force acting on the system. So if this frequency of the force or the excitation frequency acting on the system is equal to the natural frequency system, resonance happens. So it is the speed or the whirling speed is the speed at which this resonance occurs. It is not only due to the eccentricity between the rotor and the axis rotation of the shaft that causes the vibration. That causes the whirling. Whirling can happen due to the unbalanced force in the system also. If there is any unbalanced masses in the rotor or in the shaft, it will also create excessive centrifugal force. That will also lead to whirling of the shaft. You can see here a figure which represents a shaft and a rotor. The shaft is mounted on the bearings. You can see here. Okay, and if M is the mass of the rotor which is attached, this is the rotor. M is the mass of the rotor which is attached to the shaft. E is the eccentricity between the axis of rotation and the geometric center of the rotor. If this is the geometric center of the rotor, or we can say if this is the centroid of the rotor represented by G. G is the centroid of the rotor, and this is the axis of rotation. There is a small difference or small distance between these two. That is the axis of rotation and the centroid of the rotor. That distance is what is called eccentricity. Okay. Now it is due to this eccentricity when the rotor or when the shaft starts rotating. Because of this eccentricity, an excessive centrifugal force will be created. We can see here Fc is the centrifugal force which is created in the outward direction of the rotor. So it is because of this centrifugal force which causes whirling or transverse vibration of the shaft. So this is the up and down motion or the transverse vibration is what is called the whirling motion, or it is called the whirling of the shaft. So it happens at a speed which is called whirling speed or critical speed. Whirling speed is otherwise called the speed at which the vibration of shaft is at its resonant condition, or the vibration is at its resonant condition. That is, the natural frequency of the system is equal to the excitation frequency. So if M is the mass of the rotor, E is the initial distance of the central of gravity of the rotor to the axis of the rotor shaft. That is E. E is the distance between the axis of rotation shaft and the center of gravity of the rotor. And if Y is the additional deflection, you can see here when the shaft starts rotating. Here this is static condition, that is shaft is not rotating. Here when the shaft starts rotating, in addition to this gap between the centroid and the axis of rotation, there is a newly formed deflection, that is Y. This is additional deflection as the shaft starts rotating with an angular velocity omega. So Y is the additional deflection, when the shaft starts rotating with an angular velocity omega. This is that way. Okay, so the total deflection of this, or the total variation, or the total distance between the centroidal point and the mean position, or the initial position of the shaft axis, is y plus e. So y plus e is the total deflection of this centroid of the rotor and the initial position of the axis of rotation of the shaft. If k is the stiffness of the shaft, k is the stiffness of the shaft. When the shaft starts rotating, we know that excessive centrifugal force will be created due to the eccentricity between the rotor and the shaft axis, and this centrifugal force will be resisted by the stiffness of the shaft. So the resisting force is due to the stiffness of the shaft. So the centrifugal force acting which is radially outwards can be represented by Fc. You can see here Fc. Fc is equal to, we know that equation for centrifugal force mr omega square. So here the radial length, or what is the distance, total distance between the centroidal point and the initial position of the shaft axis, that is y plus e. So instead of r, it is y plus e used here. So m into y plus e into omega square, that is the centrifugal force. So this centrifugal force will be resisted by the stiffness, or the force due to the stiffness of the shaft. So resisting force of the shaft is k into deflection y. Y is the deflection of the shaft. So y is the deflection of the shaft from its mean position, and y plus e, it is a total deflection of the centroid of the rotor from the mean position of the shaft. So resisting force of the shaft is stiffness into deflection. We know that force is equal to k into x. We have k into delta that you have discussed earlier. So here delta of the deflection of the shaft is y. So k into y is the net resisting force provided by the shaft to prevent or to keep the system in an equilibrium condition, or to this is the force which tried to bring the system to its initial position. So for equilibrium position, these two forces are an equilibrium condition when the system, or this is the dynamic equilibrium condition for the system. M omega square y plus e is equal to k into y for the system to be in equilibrium position. So you can write this or rearrange the equation like this: m omega square y plus m omega square k equal to k into y, and y equal to k minus m omega square equal to m omega square into e. So y can be written as m omega square e by k minus m omega square. Okay, so I am dividing the numerator and denominator with m. So numerator then will be cancelled, and denominator it will be k by m minus omega square. We know that what is this k by m? What is stiffness by mass? It is natural frequency, square of natural frequency, omega n square. So you can write like this: omega square into e by omega n square minus omega square. So this is the expression for the deflection y of the shaft. So the deflection of the shaft y is equal to omega square e by omega n square minus omega square. This is what we have derived. Now we know that we can see here that the denominator is omega n square by minus omega. So when omega is greater than omega n, omega is actually the excitation frequency, that is the frequency of external force acting on the system. Omega n is the natural frequency of the transverse vibration of the shaft. And if omega is greater than omega n, this denominator becomes negative. So in order to make the value of y, deflection of the shaft, positive, we have multiplied this plus or minus. That is why we put here plus or minus. So I can rearrange this equation. which is equal to plus or minus e by omega n by omega all square minus 1. That is, I have divided with omega in the numerator and denominator. So this is the expression, and you can see here denominator is omega n by omega all square minus 1. When omega n is equal to omega, what is that condition called? Resonant condition. That is, natural frequency omega n is equal to omega, excitation frequency of the system. So it is the resonant condition. So at resonant condition, you can see here omega n is equal to omega. So denominator becomes 1 minus 1, that is denominator is 0. So the value of I is infinity. So it is at this situation, that is, it is at this condition, that is when omega n is equal to omega, that is at the resonant condition, the shaft will be rotating with a velocity or with a speed called whirling speed. So it is at this speed the shaft will be vibrating violently. So I am representing omega n as omega c. We know that whirling speed is represented by the symbol omega c, or omega c actually represents critical speed of the shaft, or whirling speed of the shaft. So omega n is represented as omega c by omega all square minus 1. So we found that we understood that when omega n is equal to omega, that is at the resonant condition, the shaft will be vibrating violently. So it is at that condition the speed of the shaft is what is called whirling speed. So at this condition, resonant condition, omega n is omega c, which is the critical or whirling speed of the shaft. So whirling speed of the shaft, we know the natural frequency omega n is omega c. We know the natural frequency of transverse vibration of shaft equation is root k by m. K is actually the stiffness of the shaft. It is this stiffness which resists the vibration of that shaft. The centrifugal force created due to the eccentricity of the rotor and the shaft axis is resisted by the restoring or resisting force due to the stiffness of the shaft. So it is the stiffness K, and M is actually the mass of the rotor which is attached to the center of the shaft. So stiffness, we know that stiffness of shaft is K is equal to load by deflection. Load is the load acting on the shaft. We know that here the rotor with a weight W is acting, or it is mounted to the center of the shaft, and W is the weight of the rotor which is attached to the center of the shaft. That is the load acting on the shaft. And load by deflection, it is the deflection created due to that load W, and which is what is called the stiffness of the shaft. So W by delta is equal to mg by delta. M is the central load acting on the shaft, or the central or the mass which is acting at the center of the shaft. So mg by delta is what is the load by deflection value, and which represents the stiffness of the shaft. Actually, we know stiffness of the shaft is the load required to produce unit deflection for the shaft. So load here is the central load, that is a load of the rotor which is attached to the center of the shaft. So here we can represent root k by m as mg by delta by m. So mg by delta by m is root g by delta. We can represent critical frequency in hertz, or you will get the value in hertz by multiplying this root g by delta with 1 by 2 pi. So 1 by 2 pi into root g by delta, we will be getting the natural frequency or the critical frequency in hertz. Also, if nc is the critical speed of the shaft in rotation per second, RPS is rotation per second, then we can write omega c or omega n as 2 pi nc. If you want to represent, or if you want to find whirling speed in rotation per minute, then this will be 2 pi n by nc by 60. 2 pi nc by 60 will be the whirling speed in rotation per minute. So if you want to represent whirling speed in rotation per second, then it is 2 pi nc. This is equal to root g by delta. So nc will be 1 by 2 pi root g by delta. Root g by 2 pi is 0.4985. Root g by 2 pi is 0.4985. So 0.4985 divided by root delta, rotation per second. So this is the expression for a whirling speed in rotation per second. So study this derivation. It will be it used to ask in the university examination. So after this discussion, we came to the conclusion that critical speed or whirling speed of the shaft is the same as the natural frequency of transverse vibration of the shaft. References for this session is Mechanical Vibrations by VPC, Mechanical Vibrations and Industrial Noise Control by Jithin P N, and Theory of Machines by Oscar. You can find several sold examples in these books related to this topic. Hope you understand this session. Thank you all.